In section 910, we're going to take a look at Taylor and Maclaurin series. Now, this is kind of a combination of the last few sections. Now, you should remember in the last section, we tried to rewrite a function as a over 1 minus r, where r was centered at the right spot. And I say centered at the right spot, whatever I wanted to center it at, basically. Well, not all functions can be rewritten as a over 1 minus r. Or not all functions can we have a derivative become a over 1 minus r. Or an antiderivative become a over 1 minus r. So for example, something like e to the x. F of x equals e to the x, there's really no way that I'm going to be able to rewrite that as a over 1 minus r, at least not in any easy way. Or sine x. Think of trying to rewrite a trig function as a over 1 minus r. It's just not going to happen. So we need another method. Now, our other method actually comes from what we did in section 9.7. And that was looked at Taylor polynomials. Recall that the Taylor polynomial centered at C looked like this. Each coefficient of the term was nth derivative evaluated at C divided by n factorial multiplied times x minus C to the nth power. Well, think about what that is. That's basically the first few terms. We have x to the 0th power, x minus c to the first power, x minus c to the squared power, all the way x minus c to the nth power. That's the first few terms of an infinite power series. And so if we can establish a pattern for these coefficients, and we can write that pattern in such a way as we can get, a functional notation here, then we can make this Taylor polynomial into an infinite series by just letting n go to infinity. And that's how the Taylor series is defined. The Taylor series is defined as take each term as nth derivative of f plug in c divided by n factorial times x minus c to the nth power. And obviously we're going to sum that up from n equals 0 to infinity. And just like we had in the Taylor polynomials, we call this a Maclaurin series when you center this at 0. So the Maclaurin series is the Taylor series where we are centered at 0. So that's the idea. So it's establishing a Taylor polynomial and then letting that Taylor polynomial essentially go to infinity. So let's do an example here. Let's take e to the x and let's find a Maclaurin series for f of x equals e to the x. What we have to do is start with f of x is equal to e to the x. We'll take a bunch of derivatives of this and then we're going to start plugging in 0. Again, we're plugging in 0 because my Taylor series is centered at 0, which makes it a Maclaurin series. So let's start taking derivatives. First derivative of f of x is still e to the x. That's nice. All right. And when you type in, or when you not type in, when you plug in 0, you still get 1. Now, you can see the pattern here. Anytime you take a derivative of e to the x, you just end up with e to the x power. And whatever that derivative is, whether it's the first or the second or the third, every time you plug in 0, you're going to get 1. So you get that pattern where the nth derivative, let me type it that way, of f of x is e to the x. And that means that the nth derivative when you plug in 0 will be 1. All right? So think about what that means in terms of the Taylor polynomial. Now I'm going to write out the Taylor polynomial, at least for the first few terms. But once we've established the pattern, then we'll convert that into a power series. So here's what that Taylor polynomial is going to look like. Take polynomial of whatever, however many n's we're going to get. Excuse me. And we go f of 0, that's my first term, so that's 1, plus 1 over 1 factorial times x minus 0 to the first power, plus, well, then I look at the second derivative. Second derivative, when you plug in 0, is 1. So you go 1 over 2 factorial x minus 0 to the second power, plus 1 over 3 factorial times x minus 0 to the third power. And we're going to keep doing that. Every time on top, we're getting 1 because that's what you get when you plug in 0 into every derivative of f. So you're always getting 1 on top. And then on the denominator, you're always getting n factorial. By the way, I think I've mentioned this before, but 0 factorial is 1. So you can think of it that way too. 0 factorial is 1 because you're saying there's no factors of anything. So again, multiplicative identity. So basically, let's do this. However far we go, we're going to get 1 over n factorial times x minus 0 to the nth power. And you could take that to infinity. What's that infinite series look like? Well, that infinite series is going to look like a sum. Let me pull this sum down. We're going to start at 0. We're going to go to infinity. And then it's going to be 1 over n factorial times x minus 0 to the nth power. And so notice that this is a power series. Now, just to make an observation, hopefully this will connect this to 9.8. Notice that we have two types of growth here. We have an exponential or a geometric growth with the x to the n, but then we also have a factorial growth. We know that factorial growth is a faster type of growth. That factorial is in the denominator. So this series actually converges everywhere. Converges everywhere. In other words, it converges no matter what value of x you plug in. So this is actually e to the x for no matter what value of x we plug in, right? We're saying that this power series gives you the same result as plugging in to e to the x, no matter what value of x we plug in, because it converges everywhere. Hopefully that makes sense. And this is kind of the thing that you're going to have to do. You're going to have to take those derivatives, plug in the center into each of those derivatives. Hopefully you get a pattern. And then once you establish the pattern, you can create the infinite series, coefficient times x minus c to the nth power, where this coefficient is probably going to involve derivatives, plug in the center, divided by an n factorial. All right, hopefully that makes sense. So what I'd like you to do is I would like you to try that for f of x equals 1 over x centered at 1. So push pause on this video and find the Taylor series for 1 over x centered at 1. All right, so here's what we're going to do. We're going to start with this f of x equals 1 over x, and we're going to start taking derivatives. Now, again, it's easier to take derivatives if you think of that as x to the minus 1. Minus 1 comes in front, you lower the exponent by 1, you get minus 1 x to the minus 2. Once you see that, oh, that's minus 1 over x squared, you start seeing the pattern. You go, okay, so negative 2 is going to multiply times negative 1 to give you a positive 2. Lower the exponent by 1, you get negative 3, so that's going to be 2 over x to the third. When you multiply by negative 3, you're going to get a negative 6 over x to the fourth. When you multiply by the negative 4, you're going to get a positive 24 over x to the fifth. When you multiply by a negative 5, you get a negative 120 over x to the sixth. Now, if you think about what that is, we go 1, negative 1, 2, negative 6, 24, negative 120. That's what we're getting when we plug in 1. Whoops, I've miswrote those. So that's what you end up with when you plug in 1 to all those derivatives. You end up with 1, negative 1, 2, negative 6, 24, negative 1. Now let's ignore the fact that this is jumping back and forth between positives and negatives for the moment. What you should think here is that this is actually 0 factorial. This is negative 1 factorial. And by the way, the factorial, so the negative, bring that out front. This is 2 factorial. This is negative 6 factorial. Did I say 6? 3 factorial. 6 is 3 factorial. Sure enough, 24 is 4 factorial. Sure enough, 120 is 5 factorial. And so on and so forth. So if you look at the pattern, what's happening is that this is turning into a something factorial. It's going to bounce back and forth between positives and negatives. By the way, we know how to bounce something back and forth between positives and negatives. You just take negative 1 to the nth power, right? Negative 1 to the nth power will bounce things back and forth between positives and negatives. N factorial divided by x to the, well, if I'm going with the fifth derivative, I have x to the sixth. If I go with the fourth derivative, I have x to the fifth. Notice that this is going to be x to the n plus 1 on bottom. You get 1 more than n every time. And so when you plug in 1, all we're ending up with is, again, this alternating part, negative 1 to the nth power, times n factorial. So there you go. Now, if you'd like, you can jump, now that I know this, I can jump right to the Taylor series. Because if you remember, the Taylor series is this infinite sum, n equals 0 to infinity, where we have f to the nth derivative, plug in, whoops, our value for c, divide by n factorial, and then multiply that whole thing by x minus c to the nth power. So now that I know what my pattern is for nth derivative at the center point, I can just plug in this formula in for this numerator and simplify this whole thing. In fact, let me just do a copy paste thing. So now once I've established this pattern, I can take this negative 1n times n factorial. I can plug it in right there. Notice what's going to happen. Oh, let me plug one other thing in there. We know we're centered at 1, so that'll be an x minus 1. Notice what's going to happen. This n factorial in the numerator is going to cancel out with this n factorial in the denominator. So what we're going to end up with is that. Now I'm going to clean that up just a little bit. That's negative 1 to the nth power. Okay. Hopefully, if you want an intermediate step, let me rewrite that intermediate step again, just so we're not lost. So we've taken this expression, which we know is the nth derivative of f when I plug in 1, and I replace this because obviously we're centered at 1. And then I'm canceling out this n factorial with this n factorial. And what that's leaving me is this simplified power series, this one right here. Negative 1 to the nth power times x minus 1 to the nth power. Now, obviously, this thing is going to converge not everywhere, but at certain values for x. In fact, this one converges, what would that converge? I think from 0 to 2. So from x equals, well, I should say when x is between 0 and 2, this infinite series converges, and moreover, it's equal exactly to 1 over x. So this thing, this power series, oops, is equal to 1 over x when the power series is at its interval of convergence. This one, like I was saying, the interval of convergence is when x is between 0 and 2. Okay, you can, flesh that out if you want to. But there you go. So that's how we can find a power series. Now, I hope that you remembered that we've actually done something similar to this. This one, if we would have wanted to, f of x equals 1 over x, we could have actually dealt with this one using the techniques in our last section, right? We could have rewritten that as 1 over, and then if I wanted to center this at 1, I go 1 plus x minus 1, right? And then we already have a over 1 plus r. We need an a over 1 minus r. So the way you do that in this case is you go minus a negative. That is x minus 1. And then you could put a negative on the inside. I'll call it negative 1 here. And so that is your a over 1 minus r, which, whoops, which leads you a over 1 minus r is the infinite sum from 0 to infinity. A here is 1 times, and now -1 times x minus 1, all to the nth power. By the way, you can break this up. You don't need to put a 1 in front. And then -1, you can take to the nth power. Whoops. That's not working. Let me do this slightly different then. -1, you can take to the nth power. And then x minus 1, you can also take to the nth power separately. And that's what we get. That's what we got using Taylor series. So what I'm trying to point out there is that obviously Taylor series you absolutely needed when you're dealing with e to the x. When we were dealing with 1 over x, we could have actually done that using the tricks that we saw via the geometric series in our last section. But notice that we get the same result either way. Either way, it's -1 to the n times x minus 1 to the nth power. Infinite sum from 0 to infinity. All right, let's do another. I want you to find, actually, let's skip this one. If you want to do this one on your own, go ahead and do that. That's fine. I'm going to skip this example and go straight to example number 4. By the way, the reason I'm skipping this example 3 is because that was actually one of the ones we did last section using the a over 1 minus r with a derivative, antiderivative case. If you take the derivative of f of x, you get 1 over 1 plus x, which we can deal with as a over 1 minus r. So let's skip to example 4. This is function equals e to the ix, centered at 0. Now, when we say I mean the imaginary number I. So think square root of -1, which means I squared is -1, and so on and so forth. So we're going to establish a pattern for this. Let's do this one together. So I'm going to utilize some of the work I previously did on my first example. We took derivatives of e to the x. I'm going to kind of take that a little further, but let's think what would happen if we did e to the ix. Again, I is this imaginary number. Well, if you took your first derivative, you would end up with e to the ix again, and then I would have to multiply times the derivative of the inside function. The derivative of the inside function, derivative of I times x is simply I. All right. By the way, we're talking about, again, the imaginary number I. Okay, by the way, you can do this. Obviously, we've dealt with everything so far using real numbers, but imaginary numbers, complex numbers, fine to deal with as well. Now, the second derivative, if I take a derivative of I times e to the ix, I is just a constant. It's a complex number constant, but that's still a constant. So derivative of e to the ix is e to the ix, and I'd have to multiply times another I. So you'd end up with I squared. Now, because I is that square root of -1, I squared is -1 by definition. So let's go to the third derivative. Third derivative, f third derivative of x equals, well, again, e to the ix, derivative of that is e to the ix. -1 times I is just -I. Oops. All right, fourth derivative. So what's going to happen? E to the ix, that's going to keep as e to the ix. Now here's the trick. if we do negative I times I, so negative I squared, if I square this I end up with a negative 1. Negative 1 times a negative of negative 1, or the opposite of negative 1, is just a positive 1. So I don't have to write anything. Notice where I got. I got back to my original function. My original function is just e to the ix. I ended up, after I took a fourth derivative, getting back to my original function. Now, what's that mean? Well, that means I'm going to have this pattern here where when I take the fifth derivative, I get I times e to the ix. So my fifth derivative is identical to my first derivative. And if I take another derivative, my sixth derivative is going to be identical to my second derivative. And obviously, the reason that is because how this I multiplies, right? Hopefully, we're familiar with the imaginary number I. Hopefully, you're familiar with imaginary number I. I has this pattern where you take, if you start multiplying 1 times I, or maybe it's a better way of saying this is I to a power, goes in this pattern: 1, I, negative 1, negative I. 1, I, negative 1, negative I. And you can see that this is just powers of I. So what are we going to get? Well, if you plug in, what were we plugging in? We were centering this at 0. So if I plug in 0 into my first, e to the 0 power is just 1. Plug in 0 to my first derivative, e to the power 0 is 1, but then I have to multiply times I. So you just get I times 1. I'll just call that I. Then you end up with negative 1, which again came from the fact that this was I squared. And then you get third derivative, plug in 0, negative I, which again came from the fact that this was I to the third power. And then fourth derivative, plug in 0, etc., 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 right? Fourth derivative, plug in 0, you get back to 1, which was essentially just I to the fourth. Okay? So now we've established this pattern. Hopefully you can see what's going on is we repeat this sequence. It's sort of a pattern of 4. Meaning every time I go around 4 derivatives, you get back to the same thing. Because I has this multiplicative pattern of 4. You start I to the first times another I times I to the third. I to the fourth is the identity of 1, the multiplicative identity of 1. So what are we going to get? Well, f to the nth derivative, I'm going to write this as I to the nth power times e to the ix. But again, this I to the nth power falls in a pattern of a cycle of 4. And then the nth derivative is going, when I plug in 0, is going to be I to that nth power, whatever it happens to be. So getting rid of this polynomial, well, let me do it this way. We centered this at 0, so that's fine. This polynomial, we're going to start at 1, then I, then -1, then negative I. That's what my numerators are going to do. 1, then I, then -1, then negative I. Once you get to the fourth, you get back to 1. All right. Oops. And the nth is just I to the nth power over n factorial x to the n. All right. So e to the ix, you can think of as I to the nth over n factorial times x to the n, infinite summation of that thing from n equals 0 to infinity. And by the way, once again, the factorial in the denominator is going to dominate what's going on here. And so this actually does converge everywhere. Now it converges everywhere. In this case, you can get answers that are complex numbers because obviously we have i's lying around here. So there you go. There you go. Even in the complex numbers, all of the Taylor series stuff still works. So that is example 4. Now, here's what I'd like you to do. I'd like you to find on your own the Maclaurin series for cosine of x. So find the Maclaurin series for cosine of x. We all know what that means. Push pause on the video and do that on your own. So let's take a look at this. Now, first off, let's start taking derivatives. So if I have g of x is cosine, the derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The derivative of negative cosine is a positive sine. The derivative of positive sine is cosine. So notice that after 4 derivatives, I get back to my original function again. And then I start the pattern over, right? Because we have to take the derivative of cosine, which is negative sine, derivative of negative sine, which is negative cosine, derivative of negative cosine, which is sine, and derivative of sine, which is cosine once again. And so every 4th derivative, I'm back to cosine. So I have this pattern of every 4th, I return back to my original function. By the way, we're doing the Maclaurin series, which means I'm going to center these at 0. So if you plug in 0 into g, you get 1. Anytime you plug in 0 into cosine, you get 1. Anytime you plug in 0 to sine, you end up with 0. So into sine, you end up with 0. Into cosine, you end up with 1. So negative cosine, plug in 0, you get negative 1. Sine, you plug in 0, you get 0. Cosine, you plug in 0, you get 1. Negative sine, you plug in 0, you get 0. Negative cosine, you plug in 0, you get negative 1. So we have this pattern which goes 1, 0, negative 1, 0, 1, 0, negative 1, 0. When I plug in my center into the derivatives of my function here. Now the pattern on the Taylor polynomial starts looking like this. Well, it's going to look like 1 over n factorial. You're bouncing back and forth between 1, 0, negative 1, 0, 1, 0, negative 1, 0. And then if I'd have done the 8th power, it would have started back at 1, 0, negative 1, 0. Now that's a little bit tricky to deal with. Basically, if you notice this 0, every time you have a 0, is just going to be canceled out. So if you want to, you can eliminate all of the odd powers. Let's see if I can do that. And see what we end up with is all the even powers where they jump back and forth with this numerator of between a positive and a -1. Now, that's going to be tough because if you think about my Taylor series, my Taylor series says take the nth derivative of g, plug in the center, multiply that times x to the n. Again, x to the n because we're centering at 0 over n factorial. Sum from 0 to infinity. How can I rewrite this thing by just using the even powers? Well, instead of using n here and here, what I'll do is I'll make sure that that n is forced to be an even number by taking 2n instead of that. Now, when you plug in 0, you get 0 and 0. But when you plug in 1, you get 2 and 2. Again, x squared and then 2 factorial. That matches. When I plug in the number 2, I end up with x to the 4th, and this is 4 factorial. That's what I got here. When I plug in the number 3, I end up with x to the 6th, and this is 6 factorial. And so this basically gives me all of the even powers of x. Now, we want we want the sign on all of these even powers to alternate. So I want on the numerator basically an alternating piece. So I need to stick in -1 to the nth power. And it is to the nth power because, we're starting with here plugging in a 0. If you plug in a 0, you get -1 to the 0th power, which starts as a +1. And then here, I'd plug in n equals 1. You'd get -1 over 2 factorial times x squared. That's exactly what we want. So I want to do -1 to the nth factorial times x to the 2n. And by the way, this n factorial, this 2n factorial is going to dominate. So this actually converges everywhere as well. And there you go. So I want you to do one last Maclaurin series. I want you to do a Maclaurin series now for sine. So go ahead, push pause on the video. You can utilize what you just did in the last problem and find a Maclaurin series for what I'll call h of x is equal to sine x. Right, so here's what we're going to do. Basically, if you notice, h of x, if I let that be sine of x, what's the first derivative of sine? Well, it's cosine, which is what we had for our function in the last example. So actually the pattern is going to be the exact same, although we're starting sort of one function before. So h of x, like I said, the first derivative is cosine. So what I started with as g of x, now I have as h prime of x. And so you could change the first derivative of g to the second derivative of h. Third derivative of g, or excuse me, second derivative of g to the third derivative of h, and so on and so forth. Oops, I plugged this in as a 0. That should be an x. Sorry. Now, what you'll notice is that obviously you plug in 0 because it's a Maclaurin series that we're looking for. So you plug in 0 into h, you get 0. You plug in 0 into the first derivative, you get 1. Into the second derivative, you get 0. Third derivative of h, you get -1. Fourth derivative of h, which again was the same as the third derivative of g, you get 0. So you get the 0, 1, 0, -1 pattern again. So every cycle of 4, it's going to be 0, 1, 0, -1. In this case, it's the odd derivatives that are giving you the 1s and -1s, and the even derivatives, which are giving you the 0s. So what we're going to end up with the Taylor polynomial is something that starts at 0, and then we're going to get odd exponents. So 1 over 1 factorial x to the first. My x squared term will just become a 0. And then my x to the third term will become -1 over 3 factorial x to the third. My x to the fourth term will become 0. My x to the fifth term will be 1 over 5 factorial x to the fifth, and so on and so forth. So this is just picking up the odd powers. In your Taylor polynomial. And this pattern is going to go on forever. We're just going to pick up the odd powers, and the numerators are going to jump back and forth between a +1 and a -1. Now, we knew what to do with that based on our example last time. Jumping back and forth between 1 and -1, we'll just put a -1 to the nth power in the numerator. In the denominator, instead of doing an even number always, we're going to do an odd number. That odd number is going to be 2n plus 1. So we're going to get 2n plus 1 factorial in the denominator. So that's going to give us odd factorials in the denominator. And then x to the 2n plus 1 power. And that's going to give us those odd powers here. So that's how you can deal with sine and get an infinite series, or I should say a power series, which is a Maclaurin series, which is a Taylor series for sine of x. And by the way, once again, this factorial growth is going to dominate, so this is still going to converge everywhere, right? So there we go. Now, there's an interesting observation to make, and this is why the last 3 examples were all Maclaurin series. I wanted to center the e to the ix, the cosine x, and the sine x all in the same spot. I want you to now examine those functions, e to the ix, cosine x, and sine x. And it turns out if you examine the Maclaurin series for these 3 functions, you'll see an interesting property. Actually, e to the ix is, if you write the Maclaurin series for it, it's exactly what you would get if you would have taken cosine x plus I times sine x. Let's take a look at that. Claim that this identity holds here. E to the ix is equal to cosine x plus I sine x. So I think it's easier to see if we expand out the first few terms instead of trying to write the infinite sums. So I want you to notice that e to the ix had this cyclical pattern of 4 going 1, I, -1, -I. 1, I, -1, -I in the numerator. And also cosine had this cyclical pattern of 4 where it went 1, 0, -1, 0 in the numerator. Sine had a cyclical pattern of 4, 0, 1, 0, -1. Now, if you notice, what's happening here is that the even parts of the even powers of e to the ix, I'm trying to highlight each one individually. So 1, -1 over 2 factorial x squared, 1 over 4 factorial x to the 4th, and -1 over 6 factorial x to the 6th match up perfectly with cosine x. And the odd powers, we got I over 1 factorial x to the 1st. That almost matches up with sine x, except the numerator is a 1 instead of an I. And similarly, we have a negative I for e to the ix on the 3rd power, but we have a -1 on the 3rd power for sine x. So if I just multiply sine x by the complex number I, the imaginary number I, what's going to happen is that in all of my numerators, they're going to change from 1s to i's. Let me delete that just so there you go. And now the odd powers of x coincide exactly with I times sine x. So if you add these two functions together, cosine x and I times sine x, you end up with e to the ix. By the way, the reason I'm pointing this out is that this is a really famous identity in higher level mathematics. This is one of the most important identities in all of mathematics. And what it's really doing is it's getting roots of a certain equation and it's mapping those along the complex circle. What I mean by the complex unit circle is the idea of creating an XY coordinate plane where the x-axis is the real numbers, all right? So it's the real numbers, trying to draw the real number symbol. And then the y-axis is the numbers with I. So any complex number can be written as a real number times, or excuse me, a real number A plus real number B times I, right? So any complex number can be written that way, A plus BI, and therefore you can map any complex number on this coordinate plane. So for instance, if I wanted to map on, let me go to the brushes. If I wanted to, yep, map on the number 4 plus 3i, it would be right there. Let's make that a little bit thicker so we can see that. So right there would be 4 plus 3i. Okay, so you can map any complex number along this two-dimensional grid. Now, what this circle is here, this is the circle of radius 1, so a unit circle on this complex plane. And so if I zoom into this, it turns out that any point along this circle, let's take a point maybe here. If I wanted to find that, let's undo that, make it a little bit less thick. There we go. If I want to find this point here, all I would have to do is say, well, actually, it's e to the ix. E to the ix, I go, how do I find that? Well, cosine of x gives me my how far out I should go. Sine of x gives me how far up. And by the way, when I say x, I really mean this angle here. So what I'm really doing is I'm taking each point along this unit circle and I'm saying that point has to have real number value of cosine. I shouldn't really say x, I should really say theta, where theta is the angle between the x-axis and the line going out to the point, all right? Or the line segment going out to the point. So this here is theta. I zoomed in, it's kind of pixelated, but hopefully you get the idea. So this is basically a statement. This identity here is a statement about the complex unit circle if I replace the x with a theta, all right? And it turns out that gives me a lot of really interesting things. This allows me easily to find all solutions to the equation x to the nth equals 1. All right, so if you tried to figure this out, if you try to solve this equation, obviously 1 is one solution to x to the nth equals 1, but there's a lot of complex solutions, and they can all be found by using this identity here and the fact that we're on a complex unit circle. So again, this is a really interesting identity, and it pops out of these power series. And specifically, these power series that we can only get by creating Taylor series for these functions. All right, so that is the end of chapter 9.